Okay, so today we're going to go ahead and talk about torque. So for torque, we'll use the symbol tau. Great. So it's kind of like a cursive T. So what a torque is, it's a force applied some distance from a pivot point that can cause changes in rotational motion. Okay. So I kind of think about it as just some force that makes things rotate. Or it could not make it rotate, but it would make something want to make it rotate. So the equation we use for torque is just it's a force applied some distance from a pivot. We'll oftentimes use distance from a pivot to be r. And I'm going to put in, this is F perpendicular. So F is perpendicular, is a force that is perpendicular to the object. And R is the distance of that force to the pivot point. So F and R will always need to be perpendicular. Oftentimes for units, go ahead and write down the units, and then I'll write them down. Cool. So oftentimes we'll use units for force. It could honestly be anything. We'll oftentimes use newtons though. Units for distance. We'll oftentimes use meters, but again, it could be anything. So let's kind of look at a couple examples. So let's say we have a rod. Let's say it's like a PVC pipe or something like that. Or it could be your pen or pencil that you're writing with, you're holding upright. So let's say we apply some force, some distance from the pivot. So in this case, if you apply a force some distance from a pivot, it could cause it to rotate. So the torque would be F times R. And I would encourage you, act that out with your pencil to show that it can rotate. If you're holding your pencil or pen on one end, you apply a force, it rotates. So now let's try another one. Let's apply a force straight down. So go ahead and take your pen or pencil, and go ahead and apply a force straight downwards. What happens to that pen or pencil? In that case, if you're applying a force straight downwards, it shouldn't rotate. So if it doesn't rotate, guess what the torque is? You guessed it. Torque is 0 because there is no rotation. Cool. Now let's try something else. Let's say we apply some force at an angle. Okay, so let's say we apply it. Sorry, that's not quite the angle I want. Let's say this is your force, and you apply it at a 60-degree angle, some distance, let's say r over 2 from your pivot point. And again, x is the pivot point in all these problems. So for this force, is this force completely completely perpendicular to like the lever arm? No, it is not in this case. So let's go ahead. We're going to have to break this force into our x and y components. So which force makes it? Does this thing make it rotate? Not at all. That's going to be parallel to your lever arm, r over 2, or your radius, r over 2. So it's not going to make it rotate at all. While this one right here is perpendicular, so that's going to make it rotate. So this will be, so F perpendicular is going to be what? F cosine of 60 degrees. And cosine of 60 we know is just F over 2. Cool. So the torque for this one would just be F perpendicular, which is F over 2, times the distance from the pivot, which is this, what, R over 2? So that's just FR over 4. Awesome. So we're going to go ahead and solve a couple example problems now. Okay. I encourage you to go ahead and read the problem yourself, try it yourself, and then you can check back in on the video. Great. So I'm going to go ahead and read it and draw it out. So 4 meter long, go ahead and draw that. So it's 4 meters, and it is 500 kilograms. Beam extends horizontally from the point where it has been bolted to the framework of a new building under construction. So this right here is going to be our bolt / pivot point. Okay. A 70-kilogram construction worker stands at the far end of the beam. Okay, so that's our construction worker, 70 kilograms. What is the magnitude of the net torque about the point where the beam is bolted into place? Okay, so let's go ahead and look at this. So how many objects do we have? Well, we have 2 objects, so we're going to have 2 torques. So I'm going to say, let's look at the construction worker first. So the force of gravity on the construction worker, because that's what would make it rotate, is going to be 700 newtons. So now we'll need to go ahead and find the torque of that construction worker. So that is going to be your force times your radius. So the force the construction worker is applying is straight down or perpendicular to the beam. So it's 700 times, how far away is that construction worker from the pivot? 4 meters. So that is going to be 2,800 Newton meters. And that would make it rotate clockwise. Great. So now let's go ahead and look at the beam. So for this beam, so it's a uniform steel beam. So we can approximate all the mass to be on that uniform object in the center. So force of gravity for this steel beam is going to be 5,000 newtons. So the torque is just our force times our distance from the pivot. So it's going to be 5,000 times, how far away is this beam from the pivot? Well, it looks like it's 2 meters away. Because that's, again, we draw the force of gravity vector in the center of a uniform object. So this is going to be 10,000 Newton meters. Great. So now the beam would also want to rotate clockwise. So now to find the net torque, since they're both just rotating the same way, we can go ahead and add. So it's 2,800 plus 10,000. So we get 12,800 Newton meters clockwise. Great. Okay, so we have one more problem to go ahead and try. And again, try it yourself first, and then you can go ahead and check back in on the video. Okay, so we have a 40 centimeter diameter disc below, can rotate on an axle through its center. What is the net torque of the disc about its rotation axis? Cool. So let's go ahead. We have a lot of different forces acting out. Let's go ahead and look at each one. So let's look at this 40 Newton one first. Okay, so that is going to be, let's see, how far away is that from its rotation point? It is a 40 centimeter diameter, so 20 centimeter radius. So the torque would just be, what? F times R. So it would be 40 as our force. And again, just think about a wheel and you're hitting it tangentially. That's going to make it rotate. In this case, it will be counterclockwise. So it's 40 newtons times 20 centimeters away. So 100, Newton centimeters. And again, that would be counterclockwise rotation. Cool. So we got one of them. Let's keep on going. So now let's look at this 30 Newton one. So let's see. The torque would be our force times our distance from our pivot. So our force is 30. And again, we're hitting it tangentially. So that one's going to make it rotate. I have to act it out. Is going to make it rotate. What is that? Clockwise. And again, it's 20 centimeters away because it's on the tangent, it's on the edge of the disc. So 20, so that would be 600 Newton centimeters. Cool. So let's go ahead and look at our next force. So now we have, so that's, oopsies, I forgot to write my direction. So that's clockwise. Cool. So now let's look at our next one. So we have a 20 Newton force applied like straight inwards on the disc. So if you imagine a bike wheel and you're pushing straight inwards towards like the center of the rim, is that going to make it rotate at all? No, it's not at all. So the torque in this case is going to be 0 Newton meters. Okay, so let's go ahead and look at our last force. So we have this 15 Newton of force applied at a 60-degree angle, 10 centimeters away from the pivot. Okay, so is this force applied just perpendicular or just parallel to the rotation point? Neither. So we're going to have to split it into its components of parallel and perpendicular. So in this case, I'll go ahead and draw it up here. Which part is going to make it rotate, the parallel or perpendicular? The perpendicular part is going to make it rotate. So let's go ahead and calculate that. So F perpendicular is going to be what? 15 cosine of 60 degrees, and cosine is just 1/2, so that's just going to be 7.5 newtons. So the torque, and again, it's applied at this point right here. So the torque for this one would just be F perpendicular times R, which is just 7.5 times 10 centimeters away. So 75 Newton centimeters. And again, that is going to be, so that's going to spin it this direction, which would be clockwise. Cool. Sorry, this one over here, I just realized I wrote meters instead of centimeters, but 0, 0, so I guess it doesn't matter. Cool. So now let's go ahead and find our net torque. So let me just write a little space over here. So T net. So now we essentially just need to add everything up and be careful about signs. So I'm going to call it counterclockwise negative and clockwise positive. So first one we had 800 counterclockwise, so that's going to be, I'm going to call that negative 800. Okay, our next one we have 600 clockwise. I'm going to call that positive 600. Next one is just 0, so I'll just call that 0. And then our next one we have 75 Newton centimeters clockwise. So I will again call clockwise positive. Great. So I go ahead and add this all up. Sorry, let me get a little space for myself. What? 675 and negative 800. So that's going to be negative 125 Newton centimeters. Or if I wanted to put in meters, negative 1.25 Newton meters. Cool. Thanks for solving with me.